Today we're going to take a look at new idea coming off of everything we've been learning up to this point. And the new ideas are going to be these graphs and digraphs. And as you can see, this thing called a directed graph is going to be similar to our trees that we've been working with, except it's not going to be that root and working our way down design. It's going to be like random all over the place. Some of you were talking about the traveling salesman and how we have cities located all over the place and how you would move amongst the cities. Okay, so just a couple of things. You know, when I have a digraph, it is different than a tree, doesn't need a root, and we may not have everybody connected. Okay. We also have something called regular graphs that don't have directions. And I know your eyes are down here on this picture that I have. And this one, of the two that we're talking about, and all we're going to talk about is the directed graph. You see that this is the directed graph. I have lines with arrows connecting the different nodes. So again, instead of a node that would be a tree design with the root and working from north to south, we can be all over the place with this. All right, so I have some things on here, 1, 2, 3, 4, 5, and 6. We'll call these vertices, or we'll call them nodes. And then we have the arrows, which are going to be directed arcs or edges. The big names, nodes sort of reminds us of what we were doing before. Vertices and edges are big conversation words when you're talking about directed graphs. Now, direct are sometimes called, directed graphs. I had a course in grad school, and it was graph theory, and it was an entire course because there's so much stuff with graph theory that people still haven't figured out. And one example of that is, I think a lot of you have seen this envelope, and this could come out as just being a graph. And can you draw that without lifting your pencil, without going back over a line or so on? And you start to get into some of the theory where this guy right here, this vertice has 1, 2, 3 edges. So you start talking about, well, there's 3 edges, there's 3 edges. This guy has 4 edges, 2 edges, 4 edges. And you get into the conversation in graph theory of, as long as I have an even number of what we would call odd vertices, I should be able to draw this graph. We even kind of have one in here as well. That's also 4. So you should be able to draw this without lifting your pencil because it has an even number of odd vertices. And I might as well pause for a second because I know some of you are trying to draw it now without. Anybody get it? Think if I go here to there, up to there, down to there, over there. Now, that's not going to work. Let's see. If I start and go across, up, 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 over, down, up, that doesn't work. So you keep playing because this will, in fact, work. Anybody get it yet?
Yeah.
Is that a yeah?
Yeah.
Yeah, a couple of years. Tell me where to start.
Across the bottom.
Across the bottom, like so. Go ahead.
Up diagonally.
Up diagonally. Okay.
Up diagonally again.
Up diagonally again.
Down diagonally.
Down diagonally. Not
Down diagonally again.
down diagonally again,
Then just up, right, and down.
up, right, and down. Yep. So it can be, in fact, completed that way. And there are a couple different ways, but we can do it. And the whole idea behind this graph theory is you start looking at the vertices and counting how many edges and so on and so on. There's a Bridges of Königsberg. I'm sure I'm probably butchering the spelling, but there's a whole graph theory about that, about traveling back and forth across these bridges. Can you make it? And you get into the whole no, because there are some basically vertices that I don't have an even number of odd vertices. And again, that's a grad course. There are a lot of things that aren't published that haven't been proved. Like, I just told you this and it's been proved that you can do all this, but there's a lot of stuff in graph theory that still needs to be proved. All right, so we're coming back and we're going to take a look at this directed graph I just put in front of us. And yeah, I have a node or a vertex of 1, and it goes to 5, it goes to 4, it goes to 2, and all of these different pathways. And this is just a really simple example of what's going on. So this idea comes into play also with UPS, who's really big this time of year. And a UPS driver has to make deliveries, and it gets into that, what's the shortest route? And I recently also heard it somewhere that UPS drivers, when they plan their routes of all of their stops, try to make as many left-hand turns as possible. Check that. Eliminate left-hand turns, because right-hand turns, they don't have to wait for as much traffic as a left-hand turn. And it's another component that comes into play here. Right? Some of these may have weighted paths, something that we're not going to get into. We can, so if I took this and I said, okay, let's imagine these are roads, of some sort. We can always come with a new connector. We can always add a new node. We can always add a new edge. So these guys can build just like everybody else. So if I'm going to work with a digraph, I need to start thinking about some kind of operations, like how do I construct it? Can I check to see if it's empty? How would I destroy the whole thing? Can I insert a node? Can I insert an edge? Can I delete a node? Can I delete an edge? And then the big one comes into play right here. How to search or traverse it. And an example might be, if I start in city 1 or location 1, can I get to node 3? Looks like the answer is yes. Looks like I could go several ways. I could go from 1 to 2 to 3. I could go 1 to 4 to 3. I could go 1 to 4 to 2 to 3. Start thinking about planes. I want to fly from city 1 to city 3, and I could maybe fly and have a layover in 2, and then fly to 3. I could fly from 1, have a layover in 4, fly to 2, because it might be faster to go to 2 and 3 before 4 goes to 3. Whole bunch of different ideas of what could be going on. And a simple example again is airports and flights that are booked that day. I mean, these airports are connected, but what's the time? What's the extra factor? What's the extra weight that would come into play with dealing with this? All right, so now you as a programmer, you have to start thinking about how you would program this. Okay, well, what have we been doing? Every new data type we've learned about this semester, we've looked at it 2 different ways. The first way was using some sort of array as my data type. The second was using some sort of linked list as my data type. Well, let's take a look at the first one. And this guy is called an adjacency matrix representation. Okay, so this is going to be what we're going to take a look at. And I have a nice little digraph here. with A, B, C, D, and E. And I'm starting to say, all right, so A goes to B, B goes to C, C goes to, so how can I represent this? Well, if I can go from, I'm giving them numbers. I could have left A, B, C, and E up here, but I numbered them. And if I can go from A to A, which you see down here, D to D, right? If I can go from 1 to 1, I would put a 1 in here. Well, I can't. Can I go from 1 to 2? Yes. So I have a 1. Can I go from 1 to 3? Yes. I have a 1. 1 to 4, which was the no, and 1 to the 5 is a yes. So I can represent this by putting it in this adjacency matrix. All right, let's see. 2 goes to, the only thing 2 goes to is 3. So I can fill out the rest of that row. 3, the 3 goes to 2 and 3 goes to 4. Kind of interesting. 4 goes to 4. And 5 doesn't go to anyone. All right, so I just figured out a way that I can store this digraph into something I can work with. And now within a program, I can say, which city do you want to travel from? And you say D, which I know is 4. And you say, can I get to city 2? And I'm saying, there's no way if you start in 4, you can get to 2. None at all. If I start in wherever, can I, well, what's part of the problem with this? We have lots of zeros, and that's not so good. Questions?
How do we find the fastest route
Oh, we're
for
not
all
there yet.
paths?
We still have a little bit of time to work on that. Okay.
Okay.
Yeah, we still have to go to breadth first and depth first and a whole bunch of different things. So I'm staying with this adjacency matrix, and I know this is a representation of a single path, a single flight to go from one city to another. Well, what if my question was, well, I want to start in A and I'd like to go to D, but it doesn't go directly. Is there another way to get to D? Well, here's what I'm going to do. I'm going to take this matrix. Here we go. I have 0, 1, 1, 0, 1, and I'm going to write it twice. Hopefully I won't mess it up because you're all watching. You're going to say, oh, you did it wrong. Because that's always fun to tell me when I'm wrong. Gets old after a while. I'm going to take this matrix and I'm going to multiply it by itself. I'd be willing to bet there's one of you that's putting this into your calculator right now because you know how to deal with matrices and when you multiply them. And when I multiply these two matrices, my resulting matrix, believe it or not, is going to be paths of with one stop, paths of 2. Paths of 2. So how do I multiply matrices? I'm going to fill in this location, which is row 1, column 1. And the way I get that is I take row 1 and multiply it by column 1. And I take each individual item, 0 times 0, and I'm going to add it to 1 times 0 plus 1 times 0 plus 0 times 0 plus 1 times 0. And if I add all those up, I get a 0. And then I would continue. Row 1 times column 2. Looks like I'm going to get a 1 out of that. Row 1 times column 3. Looks like I get a 1 out of that. Row 1 times column 4. So I've done this before. I don't know if any of you have or not, but that's the answers I would get. And again, I take the row times the column. I take each individual items and then multiply them and then add the results. Did I get my first row right?
Yeah.
Yep. Then I would take row 2 times column 1, and it looks like I'm going to get row 2 times column 1. I think I'm going to end up with 0, 1, 0, 1, 0. And I could keep going for the next 3 rows. And again, what's this telling me? I'm going to go back to A's. A, B, C, D, E. What this is telling me, if I want to go from A to B with one stop, I'm able to do it. If I want to go from A to B with one stop, I can do it by going to C first. Can I go from A to C with one stop? A over to B over to C. Can I get to D with one stop? A to C to D. Now, sometimes these numbers may be 2 or 3, could be a couple of different ways to go. The more nodes, the more vertices you have, the bigger these numbers will start to get. But as I made a note up here before, we have lots of zeros. Questions? This says B. B can get to B by going somewhere. B can go to C and it gets back to itself. There's one way to do it. B has one way to get to D. B to C to D. So imagine if you're doing flights and you're trying to get somewhere, and you can look at this chart and quote a rate, and then you can go to this chart from B. Say I want to go from, I should have made these letters, from B to something, and I could even take my 1 times my path 2, multiply those together and see if there are any path 3s to get somewhere. So we're like from A to D, A to B to C to D. So I can represent this with this thing called an adjacency matrix. Now, if you were getting ready to program this, you can start to see how all of these numbers, by storing them here, now all of a sudden you start, well, what if I added a new edge? That wouldn't be too hard. It would just change one of these numbers. What if I added a new node, a new vertice? I would have to add another number here and fill in the row and column that go with it. So when you start talking about inserting and some of those things, deleting, I'd have to, if I deleted city 2, it just blew up. I'd have to almost consider crossing out those lines completely and redoing my matrices. But I could do it with that. Questions? Okay, so that was our matrix representation. Our next representation is called an adjacency list. Almost sounds like linked list. List representation. And here's another data structure that we could use to represent a diagram. And if you take a look at it, same picture, but all of a sudden, what did I just draw? In my world of linked list, it looks like I drew something along the lines of, you had a class project to do this. Starts with a C. Is it that sloppy you can't read it? You're killing me. C-H-A. It's not chang. What did I have where I had an array, and in the array I stored pointers, and the pointers pointed to linked list? I have an array of pointers that point to linked list. C-H-A-I-N. Hello? Anybody? Is there anybody out there?
Chaining.
Not even an echo. Chaining, right? We could represent this. We could talk about an adjacency list representation by way of chaining. All of a sudden, I'm not wasting memory like I may have in the other one, But this boy, you know, A goes to 2, 3, and 5. If I wanted to check to see if A goes to 6, I may have to go A to 2 and come down here and see if that goes to, that kind of deal. But I can store the information by going back to an old concept that we know called chaining. That must not have been very exciting. You want to go back to drawing envelopes again, don't you? Some of you are probably still doing it.
I have a feeling that's going to be on the final, isn't it?
What's going to be on the final? That envelope.
No.
No, no envelope. All right. So if I have this fellow right here, and I say, what's the adjacency matrix? What's the list matrix? Can you draw it up? It's just a different representation. Are we back?